right. Everyone, catch you after lunch. Can I get a hello? Hello. Hey, okay, you're awake. My name is Dawn Wages, and we'll be talking about maintaining Python environments from chaos to confidence. It's a bit clickbaity. Solving Python's environment reproducibility crisis is a lot to ask for in 45 minutes, but I'll try my best to guide you through how I see the landscape, and it is constantly changing. It's really hot space right now. Hot space for Python, I guess, but it is a hot space right now, so watch the space for all of the tools that I mentioned. And it may be different in a few months, you know. So who am I? My name's Dawn Wages, she, her pronouns. I came from Philadelphia to Vermont. It's beautiful. All of the leaves are gorgeous. Thanks for bringing this for me. I am the outgoing chair of the Python Software Foundation, so my last board meeting is tomorrow. But I do a lot of work in the Python community, a lot of community organizing specifically, and I also lead the developer relations team at Anaconda. Oh, this QR code. If you feel so inclined, there will be one more QR code at the end. This is a Python packaging ecosystem survey. It is sponsored by Anaconda, but it is in collaboration with 30 plus movers and shakers in the Python ecosystem. This includes Meta, NVIDIA, Microsoft, Astral, the creators of UV, specifically PyPI and the PSF also are involved with this as well. And it is one of the first of its kind. We have 19,000 respondents and counting. It goes until the end of this year, and it's the best way for the Python packaging ecosystem to understand how you use your tools and what you'd like to see out of your packaging tools. So I really recommend you be part of that 19,000 and counting if you can. So what makes a reproducible environment? Non-deterministic builds, missing documentation, limitations of the tool chain and hidden state, platform and architecture considerations. That sounds great. And sensitive versions are part of some of the headaches that we face as we are trying to make our environments reproducible and for it to work on everyone's machine. Some of the first problems that we encounter in that exploratory life cycle are finding, I love this slide and I keep it in every presentation, so this is a little bit anomalous, but I really like to focus on that. It's a people first problem. A lot of the conversations that we want to have at the very beginning are going to be understanding that task and having a top-down approach. And it's hard to do so. I mean, every time I poll an audience, we'll talk about like whether or not we go head first into the problem and solve it as we find it. That is predominantly the main way that we solve our environment. But if you have the foresight or the colleagues to be able to help collaborate, understanding that task and trying to boil it down to its simplest component parts is really going to be a time saver. Also, active collaboration. So I come from the web dev background, so I say deploy early and deploy often, because you do have that level of complexity moving from one platform and one environment to another. And I think it's very similar to collaboration. Collaborate early, collaborate often, ask a friend or a colleague just to try out your code and open it up on whatever machine they have and see if it's as easy as you would hope it would be, because that continually brings that development lifecycle into a more concrete form. So we're going to start with a lot of slides about making decisions about our environment. And the goal of this presentation is not for everyone to absorb everything, but for this could potentially to be a point of reference on parts of really deeply technical conversations over your environment. I get into hardware architecture as well, all with very pretty designs in the slide. But if you are interested in following up on these slides, the link at the bottom is my website, and you can find a link to the slides on there as well. So here are the 5 components that we'll keep revising back to that I've boiled down environment considerations. First of which is your task complexity. What are you building, and does it contain complicated dependencies? Next are hardware considerations. These are all going to be slightly interdependent as well. It's not like cleanly cut on the division of responsibilities and where all of these lie, but these are kind of enumerating some of these thought processes. And are you going to be, in that second one, are you building with performance and optimization and publishing dev tools in mind? The third, experimentation and collaboration. As I mentioned, you want to deploy early, deploy often, share early, share often. And are you building with those quick feedback cycles to share with peers? For example, if you're building from a package repository that is known, like PyPI, that is known for having being the first place that people publish their packages, it does expedite that developer velocity, but it also means that you're using some tools that may not be well documented or well tested or have a robust ecosystem around them. Fourth is, are you building developer tools? It's not just about the tools you're using, but sometimes when you are building for a large enough audience, or you are being methodical in for example, your academic department or your company, you are building tools for your peers. And so that will also inform what tools you pick in building. And then lastly, your application development. So are you building, are you following the software development lifecycle? Are you building software around your tool? And that will also affect your environment. So here's a decision tree. I promised I would show a decision tree because that was part of my abstract. But I also don't believe that this is the best way to approach a talk. So this is more for reference, and we'll be going back and forth between this decision tree and some deeper level conversations as well. But I do want to highlight at the bottom the answers to the decision tree. We're talking about UV, pip, conda plus a container. Pixie, if people are not familiar, is a little bit newer on the scene and solves a lot of the complexities and considerations that people have with the Conda ecosystem. Conda plus the Mamba solver, so you can move a bit faster, and then Conda on the far right or left, depending on how you're looking. So, first I'm starting with binary dependencies. It's not the most, it is one of the more complicated conversations or topics to bring to people who may not be developers every day and may be using development to get past this one hurdle in their work. So let's talk a little bit more about what binary dependencies are. I start with this because it's one of the more complicated, and it will split you between the two ecosystems, mostly by format of your package. So for people who are familiar, there's the wheel format, which is going to be on PyPI, and then there's the Conda format that's going to be on anaconda.org, for example. But these are going to be two different packaging formats, the predominant formats for your Python ecosystem. So at this point, the ecosystem is always growing, and there's a new work group spinning up called Wheel Next, collaborating on what the new format for that wheel version is. And one of the considerations that people have in the Python ecosystem, or complaints that people have, and I've definitely seen it in many of the 19,000 responses so far in that ecosystem survey, is that there's not a lot of standardization across the ecosystem. So this Wheel Next initiative and PyProject.toml, which came out maybe a decade ago, but is slow for adoption, are opportunities for the maintainers of the CPython and among the ecosystem to set some of those standards. Python is an excellent glue language, so it is, many people call it the second best language for everything, which means that people also using other languages. You may see JavaScript on the front end. If you're doing software, I will be pulling from some software conversation because that's my background. But you might use JavaScript on the front end, Python could be helping with your orchestration, and then Java could be your back end talking to your database or your CMS or your infrastructure. But why are they? But why is Python difficult? Well, Python is they're Python extensions and they're compiled code. PyPI has done well with compiling C, C++, and Rust code and common packages like NumPy, Pandas, or Pillow, or self-contained binaries. Self-contained binaries means there are no conflicts within that system. Pillow will help to bundle libjpeg and libpng. But where PyPI and pip fall short are systems libraries that are outside of the Python ecosystem. So for example, if you're familiar with GDAL, HDF5, NetCDF, if not bundled, and you also have R packages, R libraries, and Julia packages that are more easily accessed in the Conda ecosystem. Also, multiple packages linking to the same system library, and sometimes there's no guarantee that there are compatible versions where they can't enforce everyone to use the same, for example, Open Blast version. So let's talk a little bit about hardware, because hardware is going to be one of the implications from your binary dependencies. There are 3 different places of responsibilities for passing up your responsibilities handling your packaging tool chain. Your system will handle your system libraries and your compiler and build tools. And this is more in the non-Conda system. There's wheel/Conda format builders. There's many alternatives, which has Python extensions and optional bundled libraries. And then the user ourselves, we will handle the requirements and installing system prerequisites. In the Conda ecosystem, Conda handles the system libraries, Conda handles your format builders, and Conda handles your requirements in solving of the discrepancies between your requirements. That is done in the pursuit of making it easier for you, but it does build high garden walls if the ecosystem is moving faster than Conda can keep up with, for example. So there are lots of thoughts. There's an incubator project, if you're familiar, called Conda PyPI. It is not maintained by necessarily Anaconda, but Anaconda employees will contribute to it. And it's kind of having a bit of a resurgence, but there is opportunities and incubator projects that are playing with the idea of how to have wheel format play nicely in the Conda ecosystem. Back to that decision tree. Let's have a quick aside into architecture and platform. This second yellow one, do you need cross-platform reproducibility? So you might need platform-specific operating systems. This will be first we're talking about operating system. That would be your Mac, your Linux, your Windows. This requires different commands to interact with the machine, and really is like the top level of this description. Then we'll go to central processing unit. This is responsible for processing instructions, and it's the brain of your computer. Compilation, if building from source, like pip and Conda build, could use more cores, which is faster builds. On old CPUs, some packages are pre-built packages which require specific CPU features. Older hardware might force source builds. And there's also a component of size bloat. So CUDA packages are massive. And so PyTorch with CUDA can be 2 to 3 gigabytes versus 200 megabyte CPU, for example. So you do want to be considerate of what your CPU is in high compute intensive scenarios. For your RAM, for complex environments specifically, especially with Conda's classic solver, you can use multiple gigabytes of RAM during your solving. This is your temporary memory that stores data while your machine is in use. Your hard drive is your computer's main storage. So a fast SSD, any tool would work fine. HDD or network storage, speed will matter. So Pixie and Mamba are typically faster in the Conda ecosystem and are better to leverage when you have limited disk space, so consider your environment size. There's going to be a massive performance difference between SSD and HDD depending on the type of compute you're working on. And I've tailored this conversation to scientific computing and academic environments. So if you do have more questions after this talk, I will not be able to stick around for the hallway track, but please find me on LinkedIn and I'd be happy to chat. And also have my fantastic colleague here who's brilliant and is full of lovely conversations, so you can find her around. Last point on this one, SSD versus HDD. There is, as I mentioned, there's a massive difference. Conda and Pixie extract thousands of small files, so HDD performance can end up being a bit painful. But with modern SSD with good specs, Pixie's aggressive parallelization will provide a lot of speed benefits. And then your motherboard, this is the main circuit board where all other components are connected and can have completely different set of instructions based on in binaries, and one may not compile for the other. And then finally GPU, these are specialized compute scenarios, but there are also GPUs. This is general processing GPUs, and people may be familiar with other more specialized processing units as well, TPUs and other things like that. In the architecture realm, so first we'll chat about disk I/O. There is a massive difference between Conda and Pixie. So HDD performance can end up being painful. I mentioned that before. For network file systems, if your home directory is on an NFS, which is really common for, this would be shared file system, common in HPC in academic settings, environment creation can be 10 or orders of magnitude greater than that slower. In disk space, Conda environments are large, multiple environments with scientific stack like NumPy, SciPy, Pandas, PyTorch. These can easily consume 50 plus gigabytes. There's also temp space. That's going to be for your package extraction needs for your temporary space, and this would be limited for temp can cause failures while you're in your processing. And next, we'll talk about memory. So for dependency resolutions in complex environments, they can use multiple gigs of RAMs. But I did mention that depending on the tool you use, there are parallel operations, and then large packages that are installing ML frameworks can also have huge memory spikes. And last on this slide, this is the last of the architecture and networking slides. I do want to talk about network HPCs and container and clouds. For bandwidth, downloading packages, especially ML and data science, could be multi-GB. There is latency. Conda Forge has mirrors, but, geographic distance can affect these speeds. And then there's also flaky connections. I think we're all maybe familiar with the conference Wi-Fi of it all. So also interrupted downloads can corrupt a package cache. For HPC, you may have limited write permissions, can't install to default locations, you'll have module systems that need to work alongside with your environment management, and then there could be job schedule constraints, building during job runs versus login nodes. And finally, container versus cloud. These can be ephemeral environments. Building fresh each time versus caching will impact your performance. And there also can be a Docker layer of optimization, and you can cache with large image sizes. Conda environments inflate container images pretty significantly, but there are optimizations for addressing those. So next I highlighted 4 more. These blue with the yellow outline are what I like to call developer experience. So we have, do you need language interoperability? Is package velocity and experimentation important? Are you working in a compliance environment? And are you using a monorepo or multiple projects with related dependencies? And so comparing these, I clearly have a bit of a favorite. Pixie is one of my favorite tools for this because it is checked in all of these attributes. You can install your Python through Pixie. Many people who are familiar with the Anaconda distribution know that through the Conda environment you can install your Python. You can also do that in Pixie, and if you've not played with UV yet, you can install Python with UV as well. Your package manager accesses the repository of packages that you need for your project, and this could be a Python package management manager. But in the experience or in the realm of Pixie and Conda, these are language agnostics. Many times this is connected to your virtual environment and the tool that you're using to create, update, and distribute. We chatted before, but an exciting part about Pixie and Conda and what it unlocks for you being a multi-language development environment is that you are able to bring in other tools that you need, and it also has it more elegantly handles some of those complicated binaries or dependencies from other languages. Log files. Log files is in the camp of, are you working in a compliance environment? And that's where my brain goes, but it's also just really beneficial as you're moving your project from one machine to another. A simple definition for those who may not be familiar, log files is a file that records every single package, that exact version, and what was on your installation environment. So this can allow for fixed or pinned ranges that keep track of the drift and solving compatibility issues. You could have per project log files that will ensure consistency, or you can have global log files. Pixie will create log files by default. And as I mentioned, this allows for better support across platforms. And then this last one, this is the last one that I'm going to be, second to last one that I'll be talking about. I just want to go back to this working in a compliance environment. Other considerations are package provenance and tracking, vulnerability tracking and scanning, being able to track against approved package lists, or having air-gapped installs. Task runners. I haven't had a lot of experience playing with different task runners. I usually have used shell scripts or makefiles. If people are familiar with maybe doing work on project, that was a pattern that I used very frequently in my early developer years. But Pixie has one out of the box. Now it is pretty simple, so I would recommend that if you are looking for something a little bit more robust, that you can leverage make, just, or task. But common activities for task runners are like building documentation, linting and formatting, package building, or running multiple versions of Python at the same time. Also CI/CD workflows. And then workspace management. This is a newer kind of trend that's happening in the ecosystem these days. The problem is that all packages could alternatively use similar dependencies, but they'll have shared utils and it's used by all of your different dependencies, and you want to develop them together, but you don't want to duplicate environments 3 to 4 times, for example. So Conda's approach has no native workspaces. You can do this in 2 different ways. You can separate your environments through isolation, or you can have a single shared environment. And I don't really recommend, again, with that, because that is a bit of a kitchen sink approach. UV's approach, though, they will have project-specific UV, and Poetry will have a project-specific workspace. And that means that it will fall within your file structure of your project. But there are workarounds for all of them. So if you are in the realm of experimenting and iterating very frequently, for all of my favorite tools, apologies I don't have a Poetry one on here, but there are workarounds to having global environments for all of them. So that would be UV work on, Pixie Global. Conda does this by default by having all of the projects in one centralized source, one centralized place, or virtual env wrapper, which is fallen out of style these days, but is a oldie but goodie. Let's think about making it reliable. So this slide has taken a bunch of different forms over the talks that I've given over the years, but it's one of my favorites. There are a lot of different, in the first generation of Python computing tools, hundreds of thousands of packages were in open source this today. you were able to leverage packages that accomplish many of the tasks that you were looking for. But the first generation focused on integrating Python's ease of use with the performance of compiled languages. So this was roughly between the 1990s and the early 2000s. You'll find tools like F2Py, which is Fortran to Python, Swig, and later CPython. There was also an emphasis on array-centric computing, introducing n-dimensional arrays, addressing Python's native list limitations for numerical data. And it also enabled mathematical operations on entire arrays without explicit loops. These were all free tools that were alternatives to using expensive proprietary tools like MATLAB, and all with academic and research origins. And so there was this culture and ethos that is born from the energy that I find in this room of building for ourselves and building for free and lowering that barrier so you can democratize some of that scientific research. This more newly adopted, widely appreciated packages in 2025 have some serious changes to the way that we're approaching what's next. It leverages days of yore. Many of them are developed by large companies or by VCs. So who's powering open source these days? Sometimes we're finding it's not just the individual contributors and the scientists hacking away on their own, but it's this whole mechanism of this ecosystem pushing it forward. Organizations are prioritizing speed and efficiency. 65% of organizations adopting or investing in AI technologies for data analytics. This is driving adoption of some GPU accelerated and high performance libraries. There's also a really interesting paradigm of zero code change philosophy. So as newer tools are coming out, there's an expectation that it would adopt a lot of a lot of the patterns that you use otherwise, and you will not have to change any of your code to experience some of those performance increases. I'm calling out Rapids on that one, but there are a few others. There's also a level of democratizing auto ML. So these are automated machine learning tools. They're becoming more sophisticated, and you get to skip some of that underlying complexity that you had to dig in earlier generations. And almost last but not least, the penultimate is making it fast. You may have noticed that there is a trend in the ecosystem of adding Rust into your tool chain. Pyo3 is Python with Rust and Python bindings. There are more packages that are leveraging Rust, like Polars, PyData, version 2, Ref, UV, and tokenizers. And then some other optimizations for speed in Python have been compiled Python implementations like Cython. There's just-in-time compilations. Similarly, like Numba, for example, is used in scientific computing and is just-in-time. There's Spy, which is a ahead-of-time compilation. And then PyPy, is a just-in-time compiler that works faster than CPython. And then last, you want to make it production ready. So this is a little bit of a hand-wavy slide. Making it production ready is never just 4 bullets. But you want to focus on being able, when you're deploying often, deploying early, sharing often, sharing early, that your environment is able to be recreated in 6 months. 6 months later, having not touched the code, not knowing what's involved in it. You'll also want to continue to update for security patches and controlled updates, and then have the ability to roll back or have an audit trail for compliance. So this is the last slide. This is us getting back to that five category considerations. And it's filled in with more bullets, more thoughts on underneath that we've all discussed in very, very high level in this conversation. Your task complexity will be based on many different caveats, some of which could be image processing or geospatial or parallel and distributed computing. Your hardware considerations goes all the way down the stack from your operating system to your GPU, CPU, binary dependencies. If you're collaborating and experimenting, you may opt for the platform and tool chain that lets you experiment quickly and iterate with the latest and greatest or untested packages as well. But there's also opportunities to think about your dependency resolution, switching between your environments, and your log files. Your developer tools may be about feedback mechanisms in your analytics, sharing with your team, and then finally your application development, if there is an application surrounding your work, thinking about production pipelines, your APIs, your persistent storage. That's me. I want you to take the survey. Please do. 19K and counting, and you can be one of those 19K. Thank you.